Section 5.1, we're going to do addition and subtraction of integers, and we're going to start with talking about what integers are. So can you guys give me what your best description of integers would be? What do you say? How are they different?
Numbers, but they also include the numbers less than 0.
All the numbers less than 0?
All of counting numbers.
Okay, so we get all the whole numbers. Let me start with those. So if we write down all the whole numbers, it would look something like this. Eventually I have to put a dot, 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 and I'll put a curly brace over here, right? And somehow I need to represent the stuff that came before. So they're the counting numbers, but they are negative. So I have something like -1 and -2 and so forth. And another way of describing that we're going to encounter, goodness gracious, let's try this again, in a moment, is these negatives, as they compare to the positive counterparts, have an actual descriptive name. They're called the additive inverse. You guys remember seeing that before? I think we've talked about it before when we were looking at whole numbers. These are the additive inverse, the number you have to add to them to get back to 0. So it's all the whole numbers and their additive inverses. That's what it really is. Okay, so these are our integer values. What I'm going to show you next is I'm going to show you different models, and there's basically 4 different models for doing addition and subtraction. And I know that you're probably not going to like all the models, and that's okay. You don't have to like all the models. Just like when we were doing different algorithms for multiplication, you don't have to like all the algorithms. But there's going to be some kid in some class somewhere, and you're going to be like, man, what was that thing that Dr. Hands did that might work for this kid? So that's kind of why I like to show you all of the different options, is because they will appeal to different people in different circumstances. So we're going to start with the chip model. Okay, so this one works really, really well for somebody who wants to actually physically hold things. And when you buy manipulatives for chip models, you can buy the fancy ones. The fancy ones will actually look like poker chips, but they're colored one color on one side and a different color on the other side. So they're interchangeable. Okay, so one of the colors is considered your positive color, and the other color is considered your negative color. All right. So usually what they use are black and red because it appeals to that financial aspect of things. So black would be which one, positive or negative? Positive. And then red was just considered negative. Think about what happens in like Microsoft Excel and stuff when you put in positive and negative numbers. I don't know if any of you guys use those for your checkbook register or something like that. They're really cool for that. But they usually use positives and negatives as black and red. So just as a reminder to start with, I'm going to do a couple of things here. I'm going to draw some images just to remind us. So here's the value that I'm going to consider positive for my picture. If you have another color with you, if you could get that out, that'd be awesome. If you don't, what you can do is you can just leave one of your circles that you are going to not color in and call that the other color. You know, so like one's empty and one's filled in. And whenever you're doing this, you really do need to give some kind of a key as to what's going on if you're using something that's sort of off of what's normally happening, right? So these are my positive and my negative. If these are what I'm using all the time, that's cool. I don't really need a key. That's understood. But if you're using pink and purple, you know, or blue and green or something like that, I need to know which is which. Makes sense? If you're using solid filled in and hollow not filled in. Okay, so what does this look like? Well, all of these look like a circle with images drawn inside of them. So you start with a circle. And what you do is you take the image that's for the positive, in this case positive 5, and I'm going to put in there 5 black dots because the black in this case is considered the positive value. So I'm going to use my black dot and I'm going to make 1, 2, 3, 4, 5. They don't have to be in an order. Okay, but you just throw them in there anywhere. So if a kid was really doing this, they would have sort of a placemat, right? You know, like a dinner table placemat or something like that, or their desktop, and they would actually put 5 black poker chips on their table. Okay, you with me? And then what are they going to put? 3 red ones. You got it. So we're going to do 3 red poker chips. Okay, after that, you have to talk about the fact that a black and a red, when combined together, equal 0. They cancel each other out. I hate the word cancel because we use it overabundantly in mathematics. But they add together to be nothing, right? These two combine, these two combine, these two combine, and they eliminate one another. So the result of this image, of this picture that you actually have, is a circle with what inside of it? 2 black dots. I didn't mean to do that. Let me try that again. Okay, so this gives me the answer 2.
Can you cross out the, are you allowed to do that?
You can cross them out. You can go like this and pull them out of the circle. Physically, what a child would do if they were working on their desk is that they would remove them. They'd pick them both up and they'd take them off the desk, right? This is sort of just my written down version of what we're trying to do. So I kind of like pulling them out with the arrows like that because that really simulates that removal process that a child would do. But any of those would be fine, Lauren. Okay? All right, so this is called the chip model. The next model is called a charge field model, and you're going to feel like, wait a minute, isn't that just what you did on the last screen? And it almost is. In this model, what we do instead of using the poker chips is we use positive and negative charges. So here's my circle again. 5. I have 5 positives, so I write 5 plus signs. Because there are 5 positives. Okay, think electricity, something like that, whatever. And then I have 3 negatives. I have the 3 negatives in here. And I pair them up exactly the same way. This doesn't have quite as much of the kinesthetic do it on your desk kind of feel to it. It does work pretty nicely in terms of this diagramming. And the idea of a positive and a negative sort of eliminating one another is really nice, whereas like black chip, red chip eliminating one another isn't really quite so obvious. You know what I'm saying? So these two combine and they eliminate one another. So these remove just like they did on the previous slide. I also don't need any colors to actually draw this one, which means of course the picture isn't as pretty, but you know, I don't need an additional marker or something like this. And then of course the answer is still 2. But it's the same model, right? We all get that. It's the same model. The next one's quite different. This is a number line model. So go ahead and draw yourself a number line. Okay? And in the number line we start at 0. Whatever the value is at the beginning, in this case it's the positive 5, it means I'm going to go right 5. If the beginning had started with negative 3, I would go left 3. Okay, so that tells me the direction I go. So this one says I'm going to move forward 5. Okay. And this right here then tells me I'm going to go left 3. So I go left 3 over here, which places me here. When I'm done, the answer then is 2. Now this also has a wonderful feel for it for the kinesthetic learners, right? You guys know what I'm saying when I say that, right? The ones who need to touch and feel things. So this classroom is set up very nicely because your desks are in rows. All right, but you could do this on the ground with tape, like masking tape. It's just awesome, right? So the idea being that I'm starting at 0, right? And I'm moving forward 5. So here's 1, 2, 3, 4, 5, right? I'm 5. And then the negative 3 says that I'm supposed to go back 3. And for the sake of what we're actually talking about, you have to be a little bit careful because we're about to introduce something in section 5.2 that's going to make this a little bit funny. But for what we're doing right now, this is really easy. I just go back 3, right? I don't care whether I'm facing forward or back or whatever, but I'm going to go 1, 2, 3 back. And my question is, how far am I from where I started? And I'm 2 away from where I started. Okay? And I don't even have to have them labeled on the number line to see that I can count them as I move. So this is a really nice one for movement in a classroom too. So it works well. Okay, any questions on the number line model? Okay. This one's really interesting. This is a pattern model. This is not a good example for this because most of your kids who are going to be quite bright are going to say 5 plus negative 3, that's just 5 minus 3. I already know how to do subtraction, right? I mean, I get that. So this isn't a great example to be using for this particular problem, but I'm going to use it because I've already got it on the screen. So what we're going to do is we're going to start with addition that we know how to actually do addition for, that is addition of 2 positive values. So I'm going to start with 5 plus 2. Okay, so 5 plus 2, of course, is 7. And the next thing I'm going to do is I'm creating a pattern. So I'm going to do 5 plus 1, and that's going to be 6, and then I'm 5 plus 0, and that's going to be 5. All of that is addition with whole numbers that you already know how to do. Okay, that's the idea of establishing the pattern. Do the addition that already know how to do. Okay, so this is somewhere around the level of maybe an end of 4th grade, 5th grade, maybe 6th grade, depending on your curriculum level of mathematics, just so that you're aware too. Okay, addition and subtraction with integers. All right, so the problem is that if you notice this, my goal is to get to 5 plus negative 3. right? And so I'm added 2, I've added 1, I've added 0. Now I'm going to add -1. And then I'm going to add -2. I'm continuing the pattern, right? The value I'm adding each time is 1 less than the one before, basically. And what I want to do over here to continue the pattern is to just go down from there. 7, 6, 5. What do I do next? 4, 3, 2. It's a pattern. I've established a pattern with something I already know how to do. This is a good example for justifying why something works, but probably not for the mechanics of doing it every time. Agreed? I mean, you're not going to create this pattern every time. But to justify to a child why this actually works, this works really well for someone who thinks with patterns. So you think about your kids that have like autism, stuff like that, right? Some of you are going to do special ed kind of things. Patterns, I mean, like they're phenomenal with patterns sometimes. So this is something that would be very appealing to a child that likes that pattern analysis. Okay, are we good? Okay. Absolute values. I promise we're going to get to subtraction, but I think it's a couple more slides in, a few more slides in. Absolute values. For any integer x, the absolute value of x is equal to x if x is greater than or equal to 0, and it's equal to -x if x is less than 0. Now, every time I teach this, people get a little bit anxious because I just told you that an absolute value is equal to something negative. But I didn't really do that. So let me show you why this definition works and makes sense, okay? So let's just use a couple of examples. Let's say you had the absolute value of 5. I know you guys know how to do absolute values with numbers in there quite easily. So what is the absolute value of 5? It's 5, right? Okay. What is the absolute value of -5? It's 5 as well, okay? So most of the time when we think about absolute values, somehow in your mind, in the back of your mind, you're thinking, I just make everything positive, right? One of the reasons that this works is because absolute values are a representation of distance. They tell you how far you are away from something, right? So it doesn't matter if I'm to the left of it or to the right of it 5, I'm 5 away, okay? So in terms of a number line, sort of a picture or something like that, here's 0 and this is 5. This is the absolute value of 5, it's the distance, and this is the absolute value of -5, also a distance. Okay, so let's make amends with why this definition actually works then, because what I just did is something that you agreed with, and nobody seemed to have any difficulty with saying just remove the negative. Well, this is an example of the first piece. If I already have a positive value, all I have to do is to remove the absolute value signs, and that's exactly what we did, right? Yeah, we just removed the absolute value signs. Well, the second one that I did was an example of the second one. I can't just remove the absolute value signs. I have to remove the absolute value signs and change the sign. And the best way that we have in mathematics to talk about changing the sign is by putting a negative on that. So if you take and you imagine this, what we actually are doing is we're taking the opposite of the -5 that's already there. When you multiply something that's negative by another negative, it becomes positive. That's what this is doing. This is saying I'm taking something that is negative and I'm multiplying it by another negative, and a negative times a negative is a positive, which I haven't justified at all yet. That's in section 5.2. Okay, so we will justify that next couple class periods from now anyway. But this is changing the signs, and changing the signs means the opposite. The other thing you can talk about is you can talk about it meaning the additive inverse. What is the additive inverse of -5? Well, it's +5. That's what that negation at the front also has meaning for us to be. The negation means the opposite of, as in the additive inverse of. Okay, so we're going to do some examples with these, and we're going to play with these signs and these images a little bit. It says to classify the following as true or false, and if it's false, we show a counterexample. Okay, so if it's true, we need to kind of think to ourselves in our mind why it works. I mean, that's a good practice to be in. But if it's false, we want to create an example that shows why it doesn't work. So if I have the absolute value of x to the 4th, what kind of a number is that? Think about this definition over here. Is it positive, like the first line, or is it negative? When you have x to the 4th, it's positive all the time, always, right? Because when you multiply something by itself an even number of times, it's positive. Negatives get eliminated. So can I just remove the absolute values then? Yes. This is true, and it's true flat out by the definition. It's true because x to the fourth is greater than or equal to 0. It could actually equal 0 if x is 0. That's okay too. That's why it's true. It's because it's a positive number. But what happens on part B? It is false. And it's false because of the exact same reason, actually. It's because it's not always a positive number. So let's give an example of one where it doesn't work. That is to say, let's say let x equal something. What would you like to let x equal? -2 should work. So if I take -2 to the fifth, what is -2? In fact, let me do it this way first. What is -2 to the fifth? So what is, yeah, let's start there. What is -2 to the fifth? It's -32 because I have 2 times 2 times 2, 5 times. And then I have 5 negatives. And when I multiply 5 negatives together, I get a negative still, right? So this is -32. And if I do the absolute value of this, what do I get? I get a positive 32 because I have the -32 and then I have the absolute value, which gives me the positive portion. And these two things, of course, are not equal. That's a counterexample. And is there anything special about -2? Well, not really. Any negative number would have worked, right? You could have chosen anything negative and the same result would have happened. This would be a counterexample. All right. C and D are awfully similar. They are not exactly the same. C says that the absolute value of x is not negative. Is that true? That is true. How is D different? Yeah. Non-negative doesn't mean positive. Non-negative means positive or 0. And that's what absolute values are, positive or 0. Right? I'm always, if we think in terms of distance, I'm always a positive or a 0 distance around anywhere from where I want to be. I plug it into my MapQuest or into my Google Maps in my phone. It never tells me I have -5 miles to go. It either says you've arrived at your destination, that's 0, right? I'm already there, distance is 0, or it tells me that I have a positive distance to go. It's telling me absolute values. However, this one down here would be false. And the example that we can create, of course, is the absolute value of 0. The absolute value of 0 is 0. It's just a distance. It means that I'm already there. I've arrived at my destination. Okay, any questions? Now, another variation that you'll see in your homework is that on some of these, they'll say, find the values of x for which the statement is true. So on the first one, if that one's true everywhere, then it would be all values of x, right? But on the second one, is it true some of the time? Sure, positive or 0, right? So if I wanted to figure out, well, when is this actually going to work? Well, it'll work when x is greater than or equal to 0, right? Absolute value of x is not negative, part C. That would be true for everything, right? It's always not negative. What about part D? That'd be true for everything except for x equals 0, right? If x is equal to 0, that's not going to work, but if x is positive or negative, it would. Okay, so you'll have some variations with those kinds of things too, where instead of classifying as true or false all the time, it simply asks you, when is it true? Okay. All right, some properties of integers. I mentioned this just a moment ago that we were going to encounter some properties again. You've seen most of these before. It's just like rehashing the old stuff you've already done. Closure is the one that everybody always gets a little bit anxious when I say. Closure means if I add to, for addition, because we are working with addition and subtraction this section, and we're talking about addition here. If I add two integers together, I get an integer. Right? I can't add two integers together and get a fraction, or add two integers together and get a decimal or something like that. That doesn't happen. I always add two integers and I get another integer. Okay? So the closure property looks something like this. A plus B. It tells me A, B, and C are integers up here, by the way. A plus B is a unique integer. We don't usually focus on the unique part, but of course that's a helpful piece of information. It is a true statement. It is unique. We only get one answer. Commutative. Do you remember what commutative looks like? Somebody tell me. What? Can you tell me, like, just tell me what I'm going to write down for me, Hannah. Okay, so A plus B is equal to B plus A, right? And it's plus because we're doing addition, right? We're doing addition with this property. What does the associative property look like? Somebody else.
A plus B in parentheses, and plus C equals A plus B plus C.
Okay. Does everybody agree with Amy? Order stays the same, ABC, ABC. There's nothing special about that particular order, but whatever order you pick, it stays the same. It's just the grouping symbols are around two different values. The identity property of integers. What is the identity element for addition? It's 0. So what this is saying is that 0 is the additive inverse I didn't mean inverse, I meant identity, sorry. Additive identity such that 0 plus A equals A plus 0 equals A. And some of you are still working on a test where you had to justify something like that. So perhaps that will help you finish that problem if you're still working on that. Okay, and then the additive inverse. This is the one I alluded to earlier. This is now true for every value in our world, because our world has just expanded to include negatives. It says that for every integer A, there exists a unique integer opposite of A, negative A, such that A plus negative A equals negative A plus A equals 0. Every number that you can give me that is an integer has an opposite value, so that when you add them together you get back to 0. So if I say 7, what's the additive inverse of 7? Negative 7. If I say negative 432, what's the additive inverse of that one? Positive 432. Okay, so it works for the positives, works for the negatives. Fantastic. All right, theorem 5.3 is next. The theorem 5.3 tells us a few helpful features about using additive inverses. If you have the opposite, right, the inverse, the additive inverse of negative A, it tells you that it's positive A, right? And again, we're going to justify in general that two negatives always make a positive. This one's just doing it for the opposite of a negation, right? Just the negative and the negative right there. If you have A is equal to B, then A plus C is equal to B plus C. We use that with equations all the time. We've seen that before as well. We saw that with whole numbers. C, however, is new because of the negatives that are involved. If you have the opposite of A plus the opposite of B, they're both negations to start with, you can simply add the values together and then take the negation of the total. Right? So if you had something like negative 5 plus negative 3, what you could do instead is you could ignore the negatives, take the 5 and the 3 and add them, and then put the negative on the result. Okay. And in fact, that's oftentimes how we describe to kids to do it anyway. I'm going to show you justifications for some different things with that. But we're going to pause right there, I believe. Let me double check on where I am. Yeah. We're going to pause right there and we're going to do group work then.